Example 2.12. A charge of 8 millicoulomb is located at the origin. Calculate the work done in taking a small charge of -2 into 10 raised to -9 coulomb from point P 003 centimeter to a point Q 04 centimeter 0 via a point R 06 centimeter 9 centimeter. Now see here, at the origin, charge capital Q, that is 8 millicoulomb, that is 8 into 10 raised to -3 coulomb, is placed. Now one point, that is 003 centimeter. It implies that we can say point P, that is at a distance 3 centimeter from the origin. So we can write distance R1 of point P, that is 3 into 10 raised to -2 meter from the origin. Similarly, second point, point Q, that is 04 centimeter 0, means second point Q, that is at 4 centimeter from the origin. So we can write R2, that is 4 into 10 raised to -2 meter. Now we want to move charge small q, which is -2 into 10 raised to -9 coulomb from point P to point Q. And in this process, what is the total work done that we want to calculate? Okay. Now, we know this thing, the work done, that is Q into delta V, means first of all we have to calculate the potential at point P, then potential at point Q, and then we have to take the potential difference between those 2 points, then Q into delta V, that is the work done. And here it is given to you via point this one. Say work done that does not depends on the path. So from which point is it is taken from P to Q, it is immaterial. Okay. Now work done, that is W equal to Q into delta V. So Q into V2 minus V1. So we can write Q into KQ upon R2, that is the potential at point Q. Then minus KQ upon R1, that is the potential at point P. So take K capital Q common. So we can write K capital Q small q into 1 upon R2 minus 1 upon R1. K, that is 9 into 10 raised to 9, capital Q, that is 8 into 10 raised to -3, small q, that is -2 into 10 raised to -9, then 1 upon R2, that is 1 upon 4 into 10 raised to -2, minus 1 upon R1, that is 3 into 10 raised to -2. Solve this one, you will get the work done to move charge small q from point P to point Q. Clear to all of you? Example 2.13. A cube of side B has a charge small q at each of its vertices. Determine the potential and electric field due to this charge array at the center of the cube. Now, when at each corner the same charge q is placed, then we know this thing, the center of the cube, that will be at the same distance from each corner. So to find out the resultant potential, first of all we have to take the potential due to any one charge and then after multiply it by 8, because total 8 corners are there. Now potential due to any one charge, that is kq upon r, where r that is the distance between corner and center of the cube, then multiply it by 8. But here each side of the cube that is given to you b, so we can write r, the distance between corner and the center, that is root 3b by 2. Now here in this equation substitute r, that is root 3b by 2, that 2 that we can take in numerator. So resultant potential we can give by the equation k q upon root 3 into b and into 16. Now we want to find electric field at the center. So electric field at the center, that will be equal to 0, because each pair of the diagonally opposite charges will cancel the electric field of each other, because due to that particular diagonally opposite pair, the electric field at the center will be equal in magnitude but opposite in direction. So resultant electric field at the center, that will be equal to 0. Clear to all of you? Example 2.14. Two tiny spheres carrying charges 1.5 microcoulomb and 2.5 microcoulomb are located 30 centimeter apart. Find the potential and electric field. A. At the midpoint of the line joining the two charges, and B. At a point 10 centimeter from this midpoint in a plane normal to the line and passing through the midpoint. Now see, two charges Q1 that is 1.5 microcoulomb and Q2 that is 2.5 microcoulomb are separated by 30 centimeter apart. See the figure. Now, first of all, we want to find the potential and electric field at the center of the line joining to these two charges. So, potential at the center, that is potential due to charge Q1 plus potential due to charge Q2. So we can write the resultant potential at point, that is kq1 upon r1. R1 that is the distance of the midpoint from Q1, which is 15 centimeter. Then plus kq2 upon r2. R2 that is the distance of the midpoint from Q2, that is also 15 centimeter. So we can say it is r. Now we can take k by r common, because r1 r2 that is r. So k by r into q1 plus q2, k that is 9 into 10 raised to 9, then r that is 15 into 10 raised to minus 2 into bracket q1 that is 1.5 microcoulomb, so that is 1.5 into 10 raised to minus 6 plus q2 that is 2.5 microcoulomb, so that is 2.5 into 10 raised to minus 6. So here 10 raised to minus 6 is taken common and it is written outside the bracket. Now solve this one, you will get the resultant potential at the center, or we can say midpoint. Clear up to this one? Now electric field at any point due to a point charge, that is given by kq upon r square. Now here both the charges are positive charges. So at midpoint the electric field due to both the charges will be in opposite direction. So we can give the equation for the net electric field, that is K Q1 upon R1 square minus K Q2 upon R2 square. Due to opposite directions, here the difference is taken. Now R1, R2, that is same, that is R. So take it common, we can write K upon R square into bracket Q1 minus Q2. Now substitute the values. K, that is 9 into 10 raised to 9. R, that is 15 into 10 raised to minus 2, square of it. Then Q1, Q2. So 1.5 minus 2.5 into 10 raised to minus 6. Solve this one, you will get the electric field. Now the direction of electric field, that will be from Q2 to Q1, because Q2 is greater than Q1. So electric field of charge Q2, that will be dominant one. So the resultant direction of the electric field at midpoint, that will be from Q2 to Q1. Clear to all of you? Now question B. At a point 10 centimeter from this midpoint in a plane normal to the line and passing through the midpoint. So here suppose we consider a point P, which one is at 10 centimeter from the midpoint in a plane normal to this line. Then from both the charges Q1 and Q2, the distance of point P, that will be same one, R dash, R dash. Now to find out the potential at this point, first of all we have to find R dash. So using Pythagoras theorem, we can calculate R dash. Now R dash, that is under root 15 square plus 10 square, then it will come to 18 centimeter. Now potential at point P. So that is potential due to charge Q1 plus potential due to charge Q2. So V dash, that is equal to K Q1 upon R dash plus K Q2 upon R dash. So that is equal to K upon R dash into Q1 plus Q2. Now substitute the values. K, that is 9 into 10 raised to 9 upon R dash, that is 18 into 10 raised to minus 2 into bracket 1.5 plus 2.5 into 10 raised to minus 6. Now solve this one, you will get the potential at point P. Now we have to find electric field at that point. Now see, magnitude wise the electric field at point P due to charge Q1 and due to charge Q2, that we can calculate E1 dash, that is K Q1 upon R dash square. So that is 9 into 10 raised to 9 into 1.5 into 10 raised to minus 6 upon 18 into 10 raised to minus 2 square. This much Newton per coulomb. Then electric field due to second charge Q2. E2 dash, that is K Q2 upon R dash square. So K 9 into 10 raised to 9. Second charge, that is 2.5 into 10 raised to minus 6 coulomb upon 18 into 10 raised to minus 2 square of it. Solve this one, you will get the electric field due to second charge, this much Newton per coulomb. Now the directions of this electric fields at point P, that will be outward as shown in the figure. Now see here, the directions at point P are as shown in the figure. Here the angle between these two electric fields, that is supposed to theta. Now here we can calculate theta from the figure. Tan theta, that is opposite upon adjacent. Now tan theta, that is 15 by 10, that is equal to 1.5. Now from the table of natural tangent, we can find theta and it comes to 56 degree and 19 minute. But here the angle between two electric fields, that is 2 theta. So multiply this one by 2. So 2 theta, that is 112 degree and 38 minute. Now the resultant electric field, that is under root E1 square plus E2 square plus 2 E1 E2 cos 2 theta. Now here substitute the values of electric fields calculated here, E1 dash, E2 dash, and the angle 112 degree and 38 minute. And then after solve this one, you will get the resultant electric field at point P, which one is at 10 centimeter from the midpoint on the plane perpendicular to the line joining to those two charges. Clear to all of you? Example 2.15. A spherical conducting shell of inner radius R1 and outer radius R2 has a charge Q. Question A. A charge small q is placed at the center of the shell. What is the surface charge density on the inner and outer surfaces of the shell? Question B. Is the electric field inside a cavity with no charge 0 even if the shell is not spherical but has any irregular shape? Explain. Now see, first question A. See, we have a spherical conducting shell having inner radius R1 and outer radius R2, and charge capital Q is already there on the shell. Now if we place charge small q at the center, then what happens? As soon as we place charge small q at the center, then the same amount of negative charge that will be accumulated at the inner surface of the cell. Now if minus q amount of charge is accumulated on the inner surface, then the same amount of positive charge will be free on outer surface. It implies that now resultantly the situation will be like this. On the outer shell, the total amount of charge will be capital Q plus small q. And at inner shell, or we can say at the surface of inner shell, the total amount of charge, that is minus q. Now surface charge density at inner shell, that is charge upon area. So sigma 1, that is minus q upon 4 pi r1 square. And surface charge density at outer shell, that is sigma 2 equal to charge on the outer shell, that is small q plus capital Q upon the surface area of outer shell, that is 4 pi r2 square. Clear up to this one? Now see, suppose we consider a cavity for which there is no charge, inside it, then if we consider a Gaussian surface very close to the surface of that cavity, then as per Gauss's theorem, we can write flux passing through that Gaussian surface, that is integration E dot dA equal to sigma q upon epsilon 0. But when inside the cavity there is no charge, it implies that the charge enclosed by Gaussian surface, that is 0, and therefore the electric field inside it will be 0. Now if the charge enclosed by the Gaussian surface is 0, then definitely the electric field will be 0 if you take any type of shape of the shell. Clear? Example 2.16, show that the normal component of electrostatic field has a discontinuity from one side of a charged surface to another given by E2 minus E1 dot n caret, that is sigma upon epsilon 0, where n caret is a unit vector normal to the surface at a point, and A is the n caret is the sigma is the surface charge density at that point. The direction of n caret is from side 1 to side 2, hence so that just outside a conductor the electric field is sigma n caret upon epsilon 0. This we will discuss later on. Next, example 2.17. A long charged cylinder of linear charge density lambda is surrounded by a hollow coaxial conducting cylinder. What is the electric field in the space between the two cylinders? Now see here, a long charged cylinder of linear charge density lambda is surrounded by hollow coaxial conducting cylinder. Here we consider the length of the cylinder, that is equal to L. Now see this inner cylinder, that is with radius equal to A, and that particular cylinder is charged 1, and linear charge density for that cylinder is lambda. Then the outer cylinder, which one is coaxial one to the inner one, that is with radius equal to B. Now we want to find the electric field in the space between these two cylinders. So for that, consider a cylindrical Gaussian surface having radius equal to small r. Now, if we consider the cylindrical Gaussian surface here, then we can understand this thing. The flux will be passing through the cylindrically curved surface, because the electric field that will be from inner cylinder to outer one. Okay. Now suppose here we consider infinitesimal small surface element at the cylindrically curved surface, then its area vector perpendicular to it, ds, that will be as shown in this figure, and electric field that is radially outward. So at that particular surface element, the area vector and electric field both will be in the same direction. Clear up to this one? Now, as per Gauss's theorem, flux phi, that is integration E dot ds, that is sigma q upon epsilon 0. Now E and ds both are in the same direction. So integration E ds cos theta, that is cos 0, that is 1. And magnitude wise, the electric field at each and every point on the cylindrically curved surface, that will be same one, because each point that will be at the same perpendicular distance r from the axis. So we can write E integration ds, that is equal to sigma q upon epsilon 0. Now integration ds, that will give you the total cylindrical surface area. So that is 2 pi RL. So we can write the left hand side E into 2 pi RL. Now charge enclosed by this Gaussian surface. So here the length of the cylinder under consideration, that is L. And linear charge density, that is given to U lambda. So we can write when charge per unit length is lambda, therefore charge in length L is how much? So that is lambda into L upon epsilon 0. So resultantly we will get electric field E, that is equal to lambda upon 2 pi epsilon 0 R. Clear to all of you? Now here if we consider this system of two coaxial cylinder as a capacitor, then for this cylindrical capacitor we can derive the equation for capacitance. Now the potential difference between two cylinders, that we can give by V equal to minus integration A to B minus E dot dr. Say, we have the relationship electric field E, that is equal to minus dV by dr. So dV equal to minus E dr. And therefore V equal to integration minus E dot dr, that we can write. And potential difference between any 2 points, that is given by the equation V, that is equal to minus integration A to B E dot dr. Clear? So as per that, this equation is written here. Now here minus minus plus E and dr, both are in the same direction. So we can simply write that is E dr, and E that we already calculated lambda upon 2 pi epsilon 0 into 1 upon R into dr. Now lambda upon 2 pi epsilon 0, that is constant one, take it outside the integration. So we can write the potential difference between two plates, that is lambda upon 2 pi epsilon 0 integration A to B 1 upon R dr. Now integration 1 upon R, that is ln R, limits A to B. First we have to substitute R equal to B, the upper limit, then minus R equal to A, the lower limit. So we can write resultantly potential difference between these two cylinders, or we can say two plates of the given capacitor. lambda upon 2 pi epsilon 0 ln b minus ln a. So that is lambda upon 2 pi epsilon 0 ln b upon a. Now as per definition, capacitance C, that is Q by V. Now Q, that is lambda into L, because length of the cylinder, that is L, and linear charge density on the cylinder, that is lambda. And substitute the value of V, that is lambda upon 2 pi epsilon 0 ln b upon A. Lambda lambda cancel. So finally you will get the capacitance C, that is 2 pi epsilon 0 L upon ln b by A. Clear to all of you? Next one. Example 2.18. In a hydrogen atom, the electron and proton are bound at a distance of about 0.53 angstrom. Question A. Estimate the potential energy of the system in electron volt, taking the zero of potential energy at infinite separation of the electron from proton. B. What is the minimum work required to free the electron, given that its kinetic energy in the orbit is half the magnitude of potential energy in A? C. What are the answers to A and B above if the zero of the potential energy is taken at 1.06 angstrom? Now see here, first if we consider the zero of the potential energy at infinite separation, it implies that now we can write the equation for the potential energy, that is K Q1 Q2 upon R1 2. Now see, charge Q1, that is charge of proton, so that is E, and that is 1.6 into 10 raised to minus 19 coulomb. Then another charge, that is charge of electron, that is minus E, that is minus 1.6 into 10 raised to minus 19 coulomb. Then separation between those two, that is 0.53 angstrom, that is 0.53 into 10 raised to minus 10 meter. Now, in first case, we have to take the zero of the potential energy at infinite. So whatever is the total work done to assemble this system is stored in it in the form of potential energy. And for that, in theory, we already derived the equation, that is K Q1 Q2 upon R1 2. So we can write U, that is equal to, now Q1 Q2, that is plus E and minus E. So our equation of potential energy will be minus K E square upon R1. So minus K, that is 9 into 10 raised to 9, E, that is 1.6 into 10 raised to minus 19 square of it, upon the separation, that is 0.53 into 10 raised to minus 10. If we solve this one, then answer will be minus 27.2 into 1.6 into 10 raised to minus 19 joule. Now, if we want to give the answer in electron volt, then we have to divide this one by 1.6 into 10 raised to minus 19. So potential energy of this system will come to minus 27.2 electron volt. Now, the kinetic energy in the orbit, that is half than the magnitude of this potential energy, that is given to you. So kinetic energy, that is half of magnitude of U. So half of 27.2, that is equal to 13.6 electron volt. Okay. Now, total energy of the system, that is kinetic energy plus potential energy. So kinetic energy, that is 13.6 electron volt. Potential energy, that is minus 27.2 electron volt. So resultantly, the total energy, that is minus 13.6 electron volt. Now, here, work done to make electron free. See here, total energy comes to negative. When total energy comes to negative, means the object is bound by this much energy. If you want to make it free, means you have to make its total energy, that is equal to 0. So if we supply the same amount of energy to it, then it will be free. And now we can say, to make electron free, we have to do work, that is plus 13.6 electron volt. Clear to all of you up to this? Now see, in first question, it was given to you the reference position that we have to take at infinity. So at infinity, the potential energy is 0. So this second term was not taken in that first question. But now in second question, it is given to you, we have to take the reference position as the separation 1.06 angstrom. And now we have to calculate the potential energy of the system, then kinetic energy, and work done to make electron free. So now potential energy, that is K Q1 Q2 upon R1 minus K Q1 Q2 upon R2. So simply we can write K Q1 Q2 into 1 upon R1 minus 1 upon R2, where R2, that is the position for the zero potential energy, that is the reference separation, that is 1.06 angstrom, that is 1.06 into 10 raised to minus 10 meter. Now Q1 Q2, that is plus E minus E, so minus Ke square into 1 upon R1 minus 1 upon R2. So minus K, that is 9 into 10 raised to 9. E, that is 1.6 into 10 raised to minus 19 whole square. 1 upon R1. R1, that is 0.53 into 10 raised to minus 10 meter. R2, that is 1.06 into 10 raised to minus 10 meter. And from this bracket, 1 upon 10 raised to minus 10 meter is taken common, so it is written here. Now if you solve this one, then you will get the potential energy in terms of joule. Then if you divide it by 1.6 into 10 raised to minus 19, your answer will be in electron volt. Now potential energy, that is minus 13.6 electron volt. Kinetic energy will be half than this one. So kinetic energy, that is half of magnitude of potential energy. So half into 13.6, that is 6.8 electron volt. Now total energy, that is kinetic energy plus potential energy. So that is 6.8 minus 13.6. So that is minus 6.8 electron volt. So work done to make electron free, that is plus 6.8 electron volt. Clear to all of you? Example 2.19. If one of the two electrons of H2 molecule is removed, we get a hydrogen molecular ion H2 plus. In the ground state of an H2 plus, the two protons are separated by roughly 1.5 angstrom and the electron is roughly 1 angstrom from each proton. Determine the potential energy of the system. Specify your choice of the zero potential energy. Now, say this one is the system of 3 charges, 2 protons and 1 electron. 2 protons are separated by 1.5 angstrom and electron is at a distance 1 angstrom from each proton. Now for a system of 3 charges, we have the equation for the potential energy, that is U equal to U12 means potential energy of a system of charge 1 and charge 2 plus potential energy of a system of charge 1 and charge 3 plus potential energy of a system of charge 2 and charge 3. So we can write the potential energy U, that is U12 plus U13 plus U23. So that is equal to K Q1 Q2 upon R1 plus K Q1 Q3 upon R2 plus K Q2 Q3 upon R2, because this distance R2 of electron from each proton, that is same one. Okay. Now Q1 Q2. So charge 1 is proton, charge 2 is proton. So charge is plus E. So first equation first step of the equation K E square upon R1. Then for second one, charge 1 that is proton, charge 3 that is electron. So minus K E square upon R2. And then for third step also, charge 2 is proton, charge 3 is electron, so minus K E square upon R2. Take K E square common, so 1 upon R1 minus 2 upon R2. Now substitute the values. K 9 into 10 raised to 9, E 1.6 into 10 raised to minus 19, square of it. Then 1 upon R1 that is 1.5 angstrom, that is 1.5 into 10 raised to minus 10, minus 2 upon R2 that is 1 angstrom, that is 1 into 10 raised to minus 10 meter, but that 1 upon 10 raised to minus 10 meter, that is taken common, so it is written here. Now if you solve this one, then you will get the potential energy of this particular given system. Clear to all of you? Example 2.20. Two charged conducting spheres of radii A and B are connected to each other by wire. What is the ratio of the electric fields at the surfaces of the two spheres? Use the result obtained to explain why charge density on the sharp and pointed ends of the conductor is higher than on its flatter portion. Now see here. When two charged conducting spheres of radii A and B are connected by conducting wire, then the distribution of charge will take place between those two spheres. The charge will be transferred from the sphere which one is at high potential to the sphere which one is at low potential. And this process will continue till potential at the surface of both the spheres becomes equal. Now, here, when these two spheres are connected by a conducting wire and the equilibrium is established, it implies that when the potentials at the surface of both the spheres becomes equal, at that time, suppose charge on sphere having radius A, that is Q1, and charge on the sphere having radius B, that is Q2. So we can write the potential at the surface of both one, that is same one, common one. So that is KQ1 upon A for this first sphere, and that is equal to KQ2 upon B, that is for second sphere. K cancelled. So we can write Q1 upon Q2, that is equal to A by B. Now we want ratio of electric fields. Now electric field at the surface of the sphere having charge Q1, that is KQ1 upon A square. For second one, we can write KQ2 upon B square. So electric field at the surface of A upon electric field at the surface of B, that is equal to KQ1 upon A square upon KQ2 upon B square. K cancelled. So Q1 upon Q2, that is, sorry, Q1 upon Q2 into B square upon A square. But Q1 upon Q2, that is A by B, that we proved. Substitute that value. So A by B into B square upon A square. So you will get the ratio of the electric fields at the surfaces of the spheres, that is B upon A. Clear to all of you? Now, second question. Okay. Explain why charge density on the sharp and pointed ends of the conductor is higher than on its flatter portion. Say Q1 by Q2, that we can write sigma 1 into A1, sigma 1, that is the surface charge density for the sphere 1, and A1, that is the surface area of sphere 1. Now Q2, that we can write sigma 2 A2. But Q1 by Q2, that is constant 1. So simply we can say sigma upon sigma 1 upon sigma 2, that proportional to A2 upon A1. It implies that sigma proportional to 1 upon A. Now, suppose we think about the flatter portion. Then for the flatter portion, the area that will be more compared to the sharp and pointed portion. And therefore, if area is more, surface charge density will be less. If area is less, surface charge density will be more. So simply we can say for sharp and pointed ends, the surface charge density will be more. Clear? Example 2.21. Two charges minus Q and plus Q are located at points 0, 0 minus A and 0, 0 A respectively. Question A. What is the electrostatic potential at the points 0, 0 Z and X, Y, 0? B. Obtain the dependence of potential on the distance r of a point from the origin when r by a, that is very much greater than 1. C. How much work is done in moving a small test charge from the point 500 to minus 700 along the x-axis. Does the answer change if the path of the test charge between the same points is not along the x-axis? Now let's discuss one by one. See here, minus q that is at 0, 0 minus a and plus q that is at 0, 0 a means we can say this is the dipole which one is coinciding with z axis. So minus q that is at a on negative z axis from the origin and plus q that is at distance a on positive z axis. Now first we want to find the electrostatic potential at the point 0, 0 z. So here consider the point on the z axis at a distance z from the origin. So to find the resultant potential, simply we can take the potential at that point due to plus q charge, then potential at that point due to minus q charge. Clear? Now see, potential at point z, that is kq upon, now the distance between that point and plus q, that is z minus a, and for negative charge the distance that is z plus a, but charge is minus q, so potential that is minus kq upon z plus a. Take kq common, so 1 upon z minus a minus 1 upon z plus a. Now by taking LCM, simplify this one. So kq z plus a minus z plus a, and in denominator z minus a into z plus a, directly we can write that is z square minus a square. Now z cancelled. So k q a plus a, that is 2a upon z square minus a square. So q into 2a, that is the dipole moment p. So we can write the potential at a point on the z axis at a distance z, that is kp upon z square minus a square. Clear to all of you? Now the point xy0, that will be on xy plane, and here this xy0 that is perpendicular to z axis, and when z is 0 means it is passing through the origin. It implies that each and every point on the xy plane that will be at the same distance from minus q and plus q. So potential at each and every point that will be 0. So we can say that is the equipotential surface. Clear to all of you? Now see, we derive the equation for the potential, that is kp upon z square minus a square. Suppose that distance z we denote by r, then we can write the equation of potential, that is kp upon r square minus a square. But if we take r that is very much greater than a, it implies that r by a that is very much greater than 1. So in that condition, we can neglect a square. So we can write v that is equal to kp upon r square, means in this case, we can write the potential proportional to 1 upon r square. Now third question, how much work is done in moving a small test charge from point 500 to minus 700 along the x-axis? Now see here, both the points are on x-axis, and x-axis that is perpendicular to the z-axis passing through the center. So potential at each point on the x-axis, that will be 0, and therefore the work done to move any test charge from one point to another point, that is q into delta v, but delta v, the potential difference, that is 0. So work done, that is 0. Then it is asked if the path is not along the x-axis, then any change will take place? No, because work done, that does not depends on the path. It depends only on the initial and final positions. Clear to all of you? Example 2.22. Figure shows a charge array known as an electric quadrupole. For a point on the axis of the quadrupole, obtain the dependence of the potential on R for R by A very much greater than 1, and contrast your result with that due to an electric dipole and an electric monopole. It implies a single charge. Quadrupole, that is an arrangement in which two dipoles are arranged back to back. Okay. Say here, this plus q charge, this minus q charge, that is one dipole. Then another dipole with minus q charge and plus q charge arranged as shown in the figure. Then this is called quadrupole. Now on the axis of it at a point P, which one is at a distance r from the center of the quadrupole, we want to find the potential. Very simple thing. We have to take the potential due to this plus q charge. Then here at the center, total charge is minus 2q. So due to this minus 2q, we have to take the potential at P. Then after again, due to this plus q, we have to take potential at P. Now, here at point P, the potential due to charge 1, that is plus q, from that the distance of point P, that is r minus a. So we can write V1, that is kq upon r minus a. Then due to charge q, which one is at, due to charge 2, which one is at center, that is minus 2q. And from that the distance of point P, that is r. So V2, that is minus 2q upon r. Then potential at P due to charge 3, that is again plus q. And from that charge, the position P is at distance r plus a. So V3, that is kq upon r plus a. So resultant potential at P, that is V1 plus V2 plus V3. So V, that is equal to kq upon r minus a minus 2 kq by r plus kq upon r plus a. Okay. Now take kq common. Therefore, V equal to kq into 1 upon r minus a minus 2 by r plus 1 upon r plus a. Now first solve these two terms with r minus a and r plus a by taking LCM here. So r plus a plus r minus a upon r square minus a square minus 2 by r as it is. Now a cancelled. So we'll get here in numerator r plus r, that is 2r, and in second term 2 is also there. So take 2 common, take it outside the bracket. So 2kq now into bracket r upon r square minus a square minus 1 upon r. Again simplify this bracket by taking LCM. So 2kq r square minus r square plus a square upon r into r square minus a square. Again take this r from denominator outside the bracket. So v, that is equal to 2kq upon r into bracket a square upon r square minus a square. Clear up to this one? Now here if we take r by a, that is very much greater than 1, it implies that compared to r square we can neglect a square. So if we neglect here a square, then from this denominator we will get r square into r, that is r cube. So we will get v, that is equal to 2kq into a square upon r cube. Means in case of quadruple, if we take r is very much greater than a, then potential proportional to 1 upon r cube. But in theory, we already discussed this thing. In case of dipole, if we take r is very much greater than a, then potential proportional to 1 upon r square. And for monopole, means for any one point charge, the potential, that is kq by r. So in that case, we can say the potential proportional to 1 upon r. Clear to all of you?